Throughout my college career, I have not had any experience with Python. I had not coded in Python, seen a script in action, or even had it installed on my laptop. Additionally, I had never worked with a Raspberry Pi before. I took this class because I knew the experience I would gain from the content in this course would be extremely beneficial to my future endeavors. The content in this course has exposed me to skills that I have already adapted into real, relevant applications, such as lane detection mapping, stoplight tracking, and my personal favorite, my own smart doorbell. Being able to combine Python scripts, Raspberry Pi hardware, and the Internet of Things was one of the highlights of my semester. So, for my final project, I was tasked with using these new skills as well as applying the LiDAR content we learned in class. I chose to map the Brennan Irieb Center for Computer Science and Engineering sign in the plaza between the Irieb Center and the Computer Science Instructional Center. I chose to map this sign because not only do I see it when I walk to class every day, but I also felt that it is a good size and shape to get a solid scan of. Lastly, being in a relatively new part of campus, I thought this would be an object that would not have been scanned by students in previous semesters. Before I could go map my object, I first had to make sure that my system functioned correctly in a controlled environment. I put my system on a tripod and 3D printed a piece that would adapt to the tripod and screwed it in. I then 3D printed bolts that would bolt the Raspberry Pi, camera, and Arduino to the mount itself. The laser then went into the Arduino while connecting to the ground and digital pin, which I then turned on. My camera was then connected to the mount, as well as my Arduino, which was powered through multiple cables that I brought with a power bank to my location. After making sure that the laser was perfectly horizontal, I mapped my golf bag in my living room. I decided on this object because in addition to being in a controlled environment where I could control the amount of light in the room, it was about the same height to width ratio as my outdoor target. I was 66 inches away, and I believed it would give me an accurate reading that matched the theoretical values I tested the previous week. After mapping my object indoors, it was time to move outside and begin mapping my real target. For this assignment, I was tasked with only mapping one side of the sign, which I was very thankful that two of my roommates and fellow 435 students came to help me for. This was a very important step in the scanning process, as it helped me identify what changes I needed to make for future scans. Multiple things stood out after analyzing these results. For starters, the streetlight directly behind the sign made the laser line incredibly faint. Additionally, any lines that did get through were crowded with noise from ambient light from the building itself. To combat these light fixtures, I needed to bring umbrellas, tarps, and potentially more hands to get a good scan. The colorpicker.py script takes an image from the Arduino and dynamically masks the image by changing the hue, saturation, and value numbers. The point of this is to isolate the red line from the laser. If I run this from a picture I took from outside, you can see here that the noise from the building and the street light make it hard for the red laser to be picked up by the color picker script. Now that we know what adjustments have to be made, I brought some more equipment to the scanning target to hopefully get a more successful scan. As you can see, I brought a tarp to drape over the sign and the camera, limiting the amount of light that can disrupt the laser's effectiveness. Additionally, I had my roommate hold a black umbrella to the side, as lower image increments had light on the side of the image. These changes made the resultant image more effective when passed through the color picker script. If we use the same color picker process we used for our initial scans, with our new scans with the tarp and umbrella, we will get a much better line than we had before. By changing these numbers, we are dynamically masking the hue, saturation, and value values that we had before. So here we have this red line that is now mostly masked, and we only get this white line here. It wouldn't be a final project if there weren't any hardware issues. My hotspot disconnected from my Pi, so I had to come back the following night to do the side. A different roommate held the tarp to the side to eliminate the street light, while another held an umbrella to mask the ambient light from the building. After going through the color picker process, I input my H, S, and V values into new data generation.py. This script goes through all 22 images I took of the front and applies the H, S, and V values to all of them one at a time. It then compiles this information into a text file of which then I can load into Cloud Compare. It also generates this plot of which I can see how well my H, S, and V values apply to all the images. When I load my text file into Cloud Compare, I can assign a color to it. This helps when I'm merging scans from different sides together. I can also filter out points that are far away. This red one is my filtered scan, whereas this white one is my unfiltered scan, and you can see lots of noise that got through Color Picker and is in the text file. To coloring, filtering, and merging my scans together, I had a full three-dimensional point cloud of the sign that I scanned. While filtering the front was easy, filtering the sides proved to be very difficult, as sometimes it would remove crucial parts of the point cloud that would disconnect it from the rest of the scan. Additionally, I was unable to get a successful scan on the back of the sign. This is because the light from the street light and ambient light from the building were unable to be fully removed from my scan. As a result, the laser line did not show up effectively on the color picker. To combat this, I duplicated my right front red scan to the back and colored it blue. This gave me something that I could attach the green and the orange scans to create my fully rendered point cloud. Another way to color my point cloud is a height ramp. This starts with blue on the bottom and then goes to green, yellow, orange, and red on the top. This verified that my angled increments from bottom to top of my scans were uniform on the front and the sides. While I was disappointed I wasn't able to fully scan the back, I was happy that for my front scan, I was able to demonstrate the curve from bottom to top of the sign. This is one of the aspects that makes the sign unique and one of the reasons that I wanted to scan it in the first place. This is the mesh that I created from my point cloud. As you can see, the front and the back maintain the profiles of their individual text files. However, the sides seem to lose that profile, and that is because of the noise that was unable to be filtered out without compromising the integrity of the point cloud itself. In conclusion, I had a wonderful experience in this course developing my own LiDAR system and mapping a point of interest of my choosing on campus. On top of the final project, I advanced skills that will for sure be of use to me as I enter the post-grad world. I thank you for a great semester and will suggest this course to all students that are looking to foster their technical skills.